First, I would like to give thanks to the organizer to give me the opportunity to present in this platform for last 2-3 years. And this is the title of my talk. This is my name and affiliation, and acknowledgement is the Roman Research Institute Library. Each and every step they are helping me immensely. The outline of the talk is as follows. At first, I would like to give an introduction to basic aspects of the topological states and the topological quantum phase transition and the matter. At the same time, the quantum spinol effect and the H state, the basic aspects of the model Hamiltonian transforming, and then the result based on the quantum theoretical study of the denomination to study. I will present here, and the conclusion finally, only the conclusion. Actually, the 2016 Nobel Prize in this physics is a strange phenomena in the matter's flatland 2D 4-dimensional system of one dimension. Basically, it does to the Professor Howlett, Ireland, and Husserl. The case list is such that discoveries are brought to the breakthrough in new theoretical understanding of the matter mystery and the order to new perspective development of associative material. The many subject and the many interesting phenomena will come through this subject in a very area. Actually, very recently I published one article in the Nature publication. A part of it I will now in your presence. At first, I would like to start my introduction. The difference between the quantum phase transition and the topological phase transition. We know the phase transition or in the quantum phase transition. Landau's theory of phase transition provides the numerical footing on which the symmetric open states can be explained. But in the past, at least 2.5 decades or near to the decade, it became clear that a series of matter with so-called topological order do not have a focal order. So this is the thing that I can. Also, the thing is this topological quantum phase transition described with the topological invariant number. It will depend on the dimensionality of the system. For 2D, it's a star number. For 1D, it's a winding number. This type of case is whether it is the positive finite and integer number. At that time, I'll case system is the topological state, non-local order parameter. But when it is the zero system is the non-topological state or the trivial state. So this is the case. But in the case of quantum phase transition or conventional transition, the thing is which have the concept of order parameter. Actually, few aspects of the topological phases of order. Just I'm going to say the topological phase of order, where the bulk is the gap, but the edge is the gapless state. Many interesting physical properties of the system are coming to the state property of the system. Although it's in bulk material, the basic conductivity channel of the state simple of the sample, and the band structure of the system is characterized by the topological number in invariant number that I told, either the Chern number or the winding number, depending on the dimensionality of the system. And also there is a very good phenomena, bulk and boundary correspondence. That is the Chern number and winding number. There is the topological invariant number, which you will calculate it from your quantum any-body physics or the quantum field theoretical calculation. You will say that will be equivalent to the number of the gapless edge mode across the system at the edge. This is also, this is experimentally verified. But this is the case you see in my the Hamiltonian is the quantum helical spin liquid. Then now my question is, what is the helical spin liquid? Actually, the helical spin liquid originated in the quantum spinol effect in a system with or without Landau level. Means either the system has applied external magnetic field or not. That is the case in quantum spinol effect. The left overs in the edge are connected to the down spin, and the right overs with the up spin, and the transport process is quantized. And this physics is generally termed as the helical liquid, which describes the connection between the spin and momentum, as we read in our master, the helicity in the Dirac equation, that is the projection of momentum in the spin direction or the vice versa. The thing is this, what is the spinol effect? Oh God, okay. What is the, hello? I'm sorry that you have not loaded my file correctly. Okay, that thing is something to say, okay, it's a one more slide is there, unfortunately. That, yes, different file extra one more, but I will explain one the how. Actually, no, let me finish. Actually, that is the Barney-Veg zoo, Barney-Veg zoo, and the hedges. And at first, the find the theoretical aspects of the single effect. Sir, may I go to board and explain? Actually, they find this type of sandwich, cadmium telluride, mercury telluride, and again the cadmium telluride, same structure. They have found it for a critical width of this quantum well, and the critical width when this is the quantum well. So is this when it is less than exceed the critical width, then the system is not in the Inall effect. But when it is exceed, then the curvature of this changing on the system, so that is Inall effect. Now the question is this: that is the Lorentz. Oh, he has quoted the correct one. Okay. Yes. And this is the correct one. Okay. The thing is, this is the correct one. You kindly see that is the sandwich structure: cadmium telluride, mercury telluride, cadmium telluride. D equal to less than EC, and also D greater than EC. D greater than EC system has some sort of this. You see the quantization, and also it has verified experimentally within 1 year of it by the Polenkamp group of Germany. And also, this is the physics of the quantum Inall effect. If one of the particles, some Harman particle, go to the left-handed direction, the other is in the right-hand direction. Now the thing is this quantum simulation process. The quantum simulation process has done by the Fu and Caney. Fu and Caney simulate the same physics. And they have done, that is the quantum Inall effect is nothing but the two copies of this conventional Hall effect is nothing but the two copies of the quantum Inall effect. You see that applied field in the up direction and the other is in the down direction. And if you see one is going one direction, the other is the counter propagating. If you add or the superimpose of it, then the system is nothing but we get without any magnetic field. One is going up and other is down, and they quantum simulate the whole process. It's a semiconductor wire, and this wire is consisting of the strong Raspberry interaction separating the SOF singlet and then applied magnetic field, and this gives finally the P plus IP superconducting system. So now the thing is a 2D system which consists of the quantum system. This Hamiltonian should be invariant time reversal symmetry and the thing is the system has a Kammer spread degeneracy. Bulk system has a dot and the topological quantum number is the Z2. And when the system is open, there is an odd number of Kammers reflected at the edge of the Fermi surface. Those are the basic criteria to get it. And now the model Hamiltonian. In this model Hamiltonian, I have done the second quantization rotation. Psi is the harmonic field, and the R is either right over and L is the left over. You see, R is the up spin, and the L is the down spin. That is the counter propagating mode with different spin. One is for the upper edge, and other is for the lower edge. And to mimic the P plus IP, that is the external applied, in the SOF spin singlet superconducting state, is induce the topological state of the matter. And this is the B is the applied magnetic field, which is also the time reversal symmetry broken source, and it is also try to destroy it, and it gives to the conventionalizing state. And this is the forward scattering thing in terms of the system parameter, and this is the arm club scattering thing. At the end of the day, I can write my whole Hamiltonian in the spin basis, and those are the spin operator, and the other in terms of this. So I have done the continuum theoretical study, abelian personalization method. This detailed calculation in my nature paper method. Okay, but here I am presenting this. This field and this field, they are the mutual field, but they are the main interesting ingredient of the transition is giving from this field. And now, okay. Now the Majorana-Ising transition I would like to present into a I write my Hamiltonian in terms of the Majorana operator basis. If I write my Hamiltonian within this transformation Majorana operator basis, I get a mass term. And this mass term you will get in terms of this. When delta equal to B, system has a Majorana transition, and we will find the Majorana transition. From this case, I have done the free energy calculation, and this is the K, is the Latin jelly liquid parameter. It's a single parameter theory. K equal to 1, system is in the non-interacting state. K less than 1, system is the repulsive state. If K is much less than 1, system is the more repulsive state. And when the K is greater than 1, system is in the attractive state. And this is the Majorana-Ising transition. This blue line is the non-interacting line, exactly solvable line, and those are the repulsive line, and those are the attractive line. And from this, the perturbative RG calculation, I have done that detailed calculation for the renormation equation. How to calculate this? It has mentioned in my paper explicitly detailed. These equations are very beautiful equation. How this equation became beautiful RG? In the RG case, the equation became beautiful depending on the symmetry, depending on the quality, and depending on the what is the behavior of the fixed plane. And if you see is the quality of this equation due to the if I change my field theta to phi, k equal to minus k, I get the same structure of the equation. And this equation has the two fixed point. One is the trivial fixed point delta 0, and another is the non-trivial fixed line delta equal to, sorry, here is k not equal to 1, k equal to half. And now I go to my RG study. I have solved this differential equation with MATLAB for k equal to 1 non-interacting case. You will see system is in the topological state. But for k greater than much less than 1, system is the strong repulsive state, and the system topological state is gradually decreasing to the 0. Now the thing is what is the value of the Amklaff patterning? The value of the Amklaff patterning is almost nil. This is the topologically protected state. And now the finally conclusion, we have presented the Majorana-Ising topological transition from the scaling analysis of the sine-Gordon coupling term, and we have derived and presented the result based on the renotion to study to predict the topological and non-topological state. And once again, I thank you to all of you, and something to say. Today my teacher, Professor Krishnamurthy, is there, and when I joined in Bengaluru as a postdoc, he taught me quantum anybody. A part of his quantum anybody physics I have learned from him, and also Professor David Amach from both of them. I have learned.
Questions?
Okay.
One should call this a helical spin liquid. It's just a quantum spin Hall state, and it's not long-range entangled, so it is not a spin liquid.
No, it's a spin liquid.
That's a comment. The question is, why can you write down the edge theory in terms of a microscopic model without anomalies? Because I thought that the whole idea is that you cannot write down an edge theory without anomaly. The theory that you wrote down seems to be anomaly-free.
Yes, of course, this is the anomaly, but I am requesting you in presence of open or PNC, I request you to read the quantum theoretical book of Fratkin in the quantum signal effect, and also the paper of the Sheila and Alexander Altland. Then you give the answer, and if you not give the answer, then my nature paper I have explicitly written how the felicity is. And I am also requesting you, just to all of you read, you will get the answer of it. Thank you, sir.